Picture this. You ask today's smartest AI to write a Python script, summarize some dense legal jargon, or, I don't know, generate a breathtaking image, and it'll nail it, flawlessly, in seconds. But ask that exact same cutting-edge model to execute a 50-step autonomous workflow, like researching a market, building a database, and deploying a website.
And it doesn't just struggle, it collapses. It forgets what it's doing halfway through and falls apart completely.
Honestly, this is the single biggest bottleneck in artificial intelligence right now. Because if we want true autonomous AI agents that can work for days at a time without us holding their hands, we absolutely have to solve this. And guess what? A fascinating new research paper has just figured out how. So you gotta wonder, why exactly do incredibly smart AI agents completely collapse on long, multi-step tasks? Now, you might be thinking the answer is that the models just aren't big enough yet, right? That we just need to throw, say, another $1 billion of compute at the problem and build a massive neural network. But actually, no, that's not it at all. The researchers behind this explainer found that the solution wasn't building a bigger, more expensive model. It was fundamentally changing how the AI perceives time and distance. Okay, let's dive into exactly what these researchers found.
Quick honesty note, because it matters for everything that follows. This isn't tested on GPT-5 running your business. It's a controlled study. Puzzles like Sudoku and a sliding block game called Rush Hour run on a much smaller model. That's deliberate. Puzzles let researchers dial difficulty up or down with total precision, isolating one variable at a time. And that one variable is the real story here.
There's this concept called the interaction budget. Basically, that's just the maximum number of steps an AI is allowed to take. But the real villain here is the effective horizon. That's the actual number of steps the AI needs to take to reach its goal. As this effective horizon gets longer, the AI's success rate absolutely plummets. It's not that the task itself suddenly got harder in terms of logic or reasoning. It's simply that the sheer distance between the starting line and the finish line caused the AI's brain to just short circuit.
You can actually see this collapse happen in real time during training. When an AI is trained on a short goal distance, it learns steadily, it gets smarter, no problem at all. But when you train that same AI on a really long goal distance, it struggles, it thrashes around, and then right around step 60, boom, total model collapse. The success rate zeroes out completely, and the error ratio just skyrockets. The AI basically starts generating complete gibberish. So exactly where and why does this old method of training break down?
Well, it breaks down because of something called the credit assignment problem. This is academic jargon for the near impossible task of determining which exact step in a long sequence of actions caused the entire thing to fail. Think of it like taking a massive 50-question math test. You do all the work, hand it in, and the teacher just hands it back with a giant red F. We've all been there, right? But imagine getting that test back with absolutely no marks on the individual questions, no partial credit, just a giant fail. How are you supposed to learn from that? How do you know if you messed up on step 4 or step 49? For an AI, this kind of delayed, sparse feedback makes it basically impossible to figure out what it did right and what it did wrong. But wait, there's an even more destructive mechanical flaw happening behind the scenes, which we'll get to in just a second.
So the absolutely crucial point here is understanding what happens inside the AI's brain when it gets that giant red F.
Here's the part that should surprise you. When a step gets punished, the model doesn't just avoid repeating it. It mathematically strips probability from that choice and scatters it across its entire vocabulary. Tens of thousands of unrelated words. In plain English, it penalizes moves it got right and randomly boosts words that have nothing to do with the task. It's not learning from the failure. It's actively unlearning its own good strategy.
And this is exactly where the researchers introduced a brilliant shift that builds a completely new paradigm. They realized they had to stop the AI from taking so many tiny, easily penalized steps. They introduced this comparison between atomic actions and macro actions. Imagine trying to navigate a massive maze. The old way, atomic actions, is like trying to solve the maze by moving one single toe at a time. It takes thousands of microscopic movements, and if you stumble even once, you fail the whole thing. The new way, macro actions, is like taking massive, confident strides. By bundling small movements into larger, logical chunks, you drastically reduce the sheer number of decisions you have to make. This brings us to the core thesis of the paper: horizon reduction. We are simply bundling small steps into bigger steps, or breaking one massive, intimidating goal down into a series of achievable mini-goals. Now, under the hood, forcing the AI to use macro actions mathematically shortens that effective horizon we talked about earlier. And by using a technique called sub-goal decomposition, we chop the total goal distance into independent segments, each with its own localized rewards. The result? The AI never wanders into that dangerous territory where error accumulation causes a total model collapse. It stays safely within a stable, highly efficient learning regime. But how you actually design these macro actions matters immensely. Finding the sweet spot is totally crucial. The researchers tested a few different structures. First, they tried forcing the AI to take fixed 5-step leaps every single time. That didn't work out so great because it was just way too rigid. The AI kept overshooting its targets. But giving the AI control over its own action granularity, meaning allowing it to actively choose whether to take a big leap or a small step, which they called flexible macro, yielded vastly superior results. Turns out flexibility is the absolute key to robustness here.
The payoff is stark. Atomic training completely flatlines on long tasks. Macro action training keeps learning, stays stable. One thing worth being precise about: the actual retrain and fix collapse result was shown up to a 4 billion parameter model. Separately, they tested whether the design itself, flexible macro actions, still holds up on frontier models like GPT-5 Mini and Gemini 3 Flash, and it generally did, though the benefit varied by model. Useful, but it's a different claim than "we fixed GPT-5's collapse." That experiment wasn't run. Fixing the collapse problem alone is a big deal. But there's a second finding here that might be even more interesting.
Here is perhaps the most mind-bending realization of this entire explainer. They call it horizon generalization. The researchers discovered that if you train an AI exclusively on short tasks using these macro actions, it suddenly masters completely unseen, infinitely longer tasks when it's actually put to the test. By stabilizing the training process and increasing the accuracy of every single step, the AI builds such a robust internal logic that it can generalize its skills to massive workflows it has literally never encountered before. We don't need to train AI on impossible month-long tasks to get them to do month-long tasks. We literally just train them perfectly on the short ones. How wild is that?
The real-world implications of this over the next 12 months are absolutely staggering. Because we finally solved this horizon bottleneck, you're going to see a rapid evolution in the AI tools you use every single day. Think radically more stable AI coding assistants that can build entire functioning apps instead of just writing individual functions. We're talking about true autonomous bots, capable of multi-day workflows without needing you to constantly hold their hands and check their work. It means AI companies can massively reduce the compute power needed for reinforcement learning, saving millions of dollars, all while outputting smarter web navigation agents that finally stop getting lost in the weeds of a simple graphical user interface. Which leaves us with a critical, really undeniable question to ponder. If AI agents can now consistently generalize to infinitely longer tasks, securely chaining together hundreds or even thousands of actions completely on their own without breaking down, what exactly happens to human oversight? Are we really ready to just hand over the keys and say, cool, check back in with me in a week? Think about that for a second. Thanks for joining me on this explainer. I really hope you found this breakdown as fascinating as I did.